Okay, so this will be the first time I'm doing this. Let me remove this. It will be me recording myself trying to solve a problem, and well, we'll see how it goes. So this problem is the last problem. It's the problem B6 from the 2018 Putnam exam, and I've never seen it before, so I'm looking at it for the first time now. I just copied it to this notepad here. Let me see if I can get rid of this. I should have probably done this earlier. Whatever. So the question is, let S be the set of sequences of length 2018 whose terms are in the set 1, 2, 3, 4, 5, 6, 10 and sum to 3860. Prove that the cardinality of S is at most this expression here. So let me think about it. So we're being asked to prove an upper bound on the number of sequences that we can find. So one thought I'm having is, suppose you had to calculate this exactly. I mean, maybe this won't go anywhere, but it feels like there should be some way of counting these things using generating functions. So you can take, some expression of form 4x5, 6 plus x to 10, and raise this to some kind of power, and then we're asking, basically we would ask for the coefficient of x to the 3860 in that kind of expression, and we would have to sort of choose x to be choose n to be big enough. So we could actually choose n to be just 3860, and so we're asking for the so this is a very I don't know if this helps or not, but it's worth writing it down here. We can factor sequence of length. Sorry. I'm doing something silly here. Length 2018. So we're looking at this. So sequence of length 2018, and whose terms are in the set. In this set, and they sum to 38060. So we're asking for this, and we can express it as minus 2018 equals. I'm trying to factor out x to 2018 from this expression because it makes it slightly more convenient to reason about. So 1860, 1842, right? Yeah. So we're asking for the coefficient of x to the this in 1 plus x squared plus x cubed plus x to the 4 plus x to the 5 plus x to the 9, and the power is the same. So how can we get estimates on this? I mean, it seems kind of very unwieldy as an expression, so not sure if it's the correct approach to be taking here. So obviously we could compute this kind of coefficient just differentiating this like 100, I mean, by this number of times, and that would zero out all the previous terms, and we could set like x equals 0 to kill everything else and evaluate some kind of big derivative. But the problem is this expression is not going to, I don't think it's going to have very convenient derivatives. That's the issue. So we can't really reason about it through that kind of mechanism, I don't think. Obviously, this is kind of a nice expression because it's x to the 6 minus 1 divided by x minus 1, but I don't think that would go anywhere. So anyway, I like looking at this expression. We have 2 to the 38, so 3860. So let's first think, can we prove that it is at most 2 to the 3860? So 2 to the 3860 is the number of subsets of a set of 3860 elements. And we are looking for yeah, I'm not sure actually. I'm not sure how you would see that. Let's take some other approach. So suppose that we define a function, something like this, which is the, well, let me write it like this. Right. So this is a kind of an easy thing, and we know something is about this function. So we know that if we ask for this, then it's equal to 1 for. So it's a kind of a boundary condition, and if n s equals 0 for s less than n. So those are some boundary conditions, and we also know that if we are asked f and s, we can sort of assume that the last element of the sequence is one of these, and then we'll get some kind of sum expression. 1 plus s minus 2, you know. kind of annoying to write out, but right. So we have some function that satisfies this. So we might ask, can we get some kind of bounds on this function? Sort of, we know it on a triangular region, and we are trying to work out its value. We're trying to use this sort of relation to extend it. So this is a way we could compute the cardinality if we had to. So we could use this to compute it exactly using dynamic programming or something like that. And I think in this case it would be efficient because we wouldn't need to compute that many elements. But the question is, can you get some kind of bound? Like, if you have this kind of recursion, how do you get a bound on f from above and try to sort of prove it by induction? So the bound we were given seems to be of a particular form. So it's like 2 to the s. So can we show that this is bounded from above by 2 to the s? And I think we can. So we can show it by, assume that these are all bounded by 2 to the s, right? Then this side is going to be less than or equal to some sum like 2 to the s minus 1 plus 2 to the s minus 2 and so on. And this is going to be definitely less than 2 to the s. So we can get a proof using induction, and we know that it's true, obviously, for all of these values. So we know that it's strictly less than 2 to the s. Well, we can't prove it strictly because, well, if n and s are both positive, right, then I think we can prove it using this argument, basically, that we have this inequality. So we can get this part, but then we are supposed to get this factor. And now I'm guessing sort of where's 2048 coming from, right? So, so one place it could be coming from is that the sum of these guys is 31. So 6, 12, 21, 31. So it could be coming from that sum, right? So we could sort of make a guess that the bound is going to be of the form is going to be less than or equal to 2 to the s times n over n plus 30 raised to the power of n. Right? So this is the conjecture. Now, can we prove this? And the idea is to try to prove it so obviously I'm trying to check if this is just holding for all of these values. So obviously if s is less than n, then, so suppose we only work with s and n positive, so strictly positive, 1 and above, then obviously if s is strictly less than n, then this is going to be 0, and this is going to be something non-zero. So in that case, we're going to be safe, and this bound is going to hold for sure. And if we have n and n, then this bound will look like 2 to the n times n over n plus 30 to the power of n. So it will be like 2 to the n times 1 minus 30 over n plus 30 to the power of n. And the question is, can we show that this is always greater than 1? well, we can't really show that it's always greater than 1, actually, because if you plug in like n equals 2 or something, then this is just going to be very, very small. So we can't really show that. So this conjecture actually does not work. We can't actually prove, we can't prove this statement. Because suppose, take n equals 1, then it's just, it's obviously going to fail if we pick n equals s equals 2 or something like that. I mean, it's we're supposed to get 2 here. Well, yeah, we're supposed to get 2 here, and this will be like 4, but then we will have like here 2 over 32 and we'll square it, so this will be very tiny. So it's not going to work. This conjecture is false. So we have to look for something slightly different. So can we bound it instead by, but that would not be tight enough anyway. Yeah, it would not be tight enough. I thought maybe you can bound it by directly by this expression. But even if we did that, like this is probably much smaller. So it would not be worth it to do that. So the logic of this argument is very persuasive, but so we're supposed to improve on that somehow. But I'm thinking, so I don't really want to. It would be nice if we didn't have to guess a functional form for the upper bound and then prove it by induction. I mean, I'm guessing now that if we can guess the right form, then we'll have no trouble. And it seems clear that, like from this expression, the right form has something like this, like, and then there's just this, like this 2048 that I don't understand where it's coming from. Like, where is 2048 in this problem, right? I mean, it doesn't seem obvious. Actually, let's compute this. So we know that we are going to get some expression like this. And I'm now curious what this expression exactly is. So this is, suppose we write it as a multiple of 2 to the s minus 10. So we're going to have something in binary, basically. We're going to have, so here we're going to have 2 to the 9, 2 to the 8, 2 to the 7, 2 to the 6, 2 to the 5. So 1, 2, 3, 4, 5, 6. And then you're going to have 2 to the 4. And then we're just going to have 1. So we're looking at this. And this is 2 to the s minus 10 times 2 to the 10 minus. So if you add 2 to the 3, 2 to the 2, 2 to the 1 plus 1, then that will be 2 to the 10 minus 1. And we'll also subtract 8 for 2. So that's going to be 14. So we're going to get this. Okay. So this is sort of measuring sort of how far away. So we get this 15, which is interesting. Yeah. Oh. Yeah, hold on. So minus 15 equals 1009 over 1024, which is 2018 over 2048. Okay, so this is where it comes from. All right, so I figured out where this mysterious fraction is coming from. So then, oh, okay, hold on. So then we are supposed to take that. Okay. So, yeah, that's very confusing. Yeah, because this 2018 and this 2018 are not the same thing. They're not coming from the same place. So that's why my guess of the form was just very off. So the correct form is this 2018 over 2048 is just this expression here, and then we have this n here. So the new conjecture is is bounded from above by this expression. And we can write this as 15 over 2024, right? And so now we can check sort of the base case. If we have s equals n, then we're going to get 2 to the n. Actually, this might be, I'm thinking if it's more convenient to put it in the other form, but I don't know. Anyway, we're going to get this. So we want to show this is always greater than or equal to 1. So we want to prove this. Right. And suppose we put n equals 1, well, that's obvious, it's greater than or equal to 1. And it seems kind of obvious that we can prove something like this by showing that the expression is increasing. So suppose we take a derivative here with respect to n, and we're going to get 2n log 2 times this. Oh, sorry, we don't even have to do that. Yeah, sorry. Because, yeah, this is just 2 times 1 minus 15 over 4n. And this is just a, this is just greater than 1, so this is always greater than or equal to 1. So, actually strictly greater than 1 even. And if we allow n to be 0, then it's greater than or equal. And I think we'll never really need that case, but basically the idea is that the induction base case holds. So we know that this statement holds across the triangle s is less than or equal to n. And we now have one to reason about s greater than n. And now we're basically going to do the argument that I did here. So suppose we start with ns. We know that this equality holds, right? And so we're going to use the induction hypothesis now. And we're going to say 1 minus 15 over 4 n minus 1 times, we're going to get some sum here, and the sum will be 2 to the s minus 1 plus, so it will be just this, 2 to the s minus 10, which will be equal to 1 minus 15 over 10 to the 24 to the n minus 1 times this expression we have computed here, which will be equal to 1 minus 15 over 24 times to the n times 2 to the s. And that finishes the proof by induction. And to get this claim here, we're just going to set specialize this identity, and we're going to get times 1 minus 15 over 10 to the 4 18. And this will just give us, so this is 1009 or 1024 as I did before, which is the 2018 or 2048 if we expand by 2. Okay, so that's the solution to this problem, and I hope you enjoyed this problem solving session. I might do more. I mean, this was a interesting problem. I mean, I get sidetracked here. I thought generating functions might help, but actually it's just, you just deal with this dynamic programming relation. And the 2 to the s bound is easy to spot, and then you just have to improve it by noticing that, by doing this computation basically. And then you can, so something that throws you off, and which was probably intentional, is that when you look at this expression, the upper bound you're likely to guess is going to treat these two 2018s symmetrically. But actually, you're not supposed to do that. Actually, this 2018 and this 2018 are coming from different places. This 2018 is coming from the length, while this 2018 is coming from basically the 1009 that you get here. It's coming from 2 to the 10 minus 15, which is the stuff you left out here of the binary expansion. So it's a very tricky way to phrase the problem, but that gets you to chase down not a very productive form for the upper bound. But once you notice it, then it's not difficult to prove it. So thanks for watching again.